Simple acid-base titration from May-June 2015 variant 3.3. In this question, they have said HA is an organic acid. We can understand that any acid has H plus ion, therefore HA means A could be any anion, just like Cl minus, like NO3 minus. So any anion could be represented by A. So HA is a general form of writing any acid. So here they have said HA is an organic acid. Solution of Fa1 was prepared by dissolving 13.1 grams of solid acid in each decimeter cube of solution. You are to determine the relative molecular mass MR of acid by titration with aqueous sodium hydroxide. The equation for the reaction between acid and sodium hydroxide is given below. So here is the equation. Fa1 is a solution containing 13.1 grams per dm cube of organic acid, as they have said in the introduction. Fa2 is 0.1 molar sodium hydroxide solution. In this case, we have bromothymol blue as indicator given. Reagent and apparatus given for this experiment are Fa1 solution, Fa2 solution, bromothymol blue as indicator with a dropping pipette. Then we have a burette and a pipette of volume 25 centimeter cube with a pipette filler. Then we have a retort stand here with white tile and a conical flask with a funnel. Method says fill the burette with Fa1. So let's fill the burette first. Now fill the burette with Fa1. So to fill this burette, we need to close this knob first by twisting it to the clockwise. So you can see in the space, if it is revolving anti-clockwise, the space is opening up, and if you close it like a normal tap, twisting it towards the right, the tap is closing. So we will close it first, and now we will put a funnel here and we will pour our Fa1 solution through this funnel into the burette slowly. Burette is not yet filled. Why? Because if you look at the bottom end of the burette, this column needs to be filled also, because once you open this tap, this liquid will first go here. Okay, so this needs to be filled also. So let's open this first to remove the air from here. Open it first and then close. It means this column is now filled with the solution. Now we will make the level of this Fa1 to this 0 mark. So here you can see the 0 mark is here. This is 0 mark. We need to fill the liquid up till here, up till this mark. So let me fill again. If the solution gets a bit higher than that level, you can drain out a bit of solution. Now the mark is exactly 0. So this is our initial burette reading 0.00. One more thing to tell you here is the least count of the burette from the graduations given can be seen that it is 0.1, because this is 1 cm cube, 0 to 1, this is 1 cm cube, and we have 10 readings here. It means each graduation is 0.1. So if each graduation is 0.1, we will measure its reading up to 0.05, which is in between these two. Therefore, the least count of this burette, which is written here also 0.1, divided by 2, we will get the error, that is 0.05. So all the burette readings will be recorded up till 2 decimal place. In this case, we will record here the reading as 0.00. Now let me hold this burette in the retort stand here and keep it at a level that you can add solution from this into this funnel easily. So you can add from here using this knob. So its level must be like this much higher from the white tile. Now the next point says use the pipette to transfer 25 centimeter cube of Fa2 into a conical flask. This is our pipette. Pipette has two ends, one is narrow and the other one is broad. There is a mark from the broad end, from the broad end there is a mark. Here is the mark, you can see this mark. If you fill this from here up till this mark, up till here, this mark, the volume taken will be exactly 25 centimeter cube. Now, how to use this pipette? We will use a pipette filler. Now, what is pipette filler? Pipette filler is an apparatus that is used to fill the solution in pipette. It has 3 buttons. One is here, that is A. Then the button here is S, suction, and there is a button here E, which is eject. So what we need to do here is, first of all, we will attach this pipette filler at the top from this end. We will make sure that we can use it with one hand and it will not fall. It's tight enough. Now, we will press this A button and we will squeeze this bulb. Now we will release this A button and the bulb will remain deflated. Now it can suck the solution up. Now we will put this pipette into the solution, Fa2 we have to take. Now I will press here this S button. So as soon as I will press this S button, suction of solution starts. So you can see the solution is starting to come up, and I have to stop it at this point where there was a mark. Then I will transfer this content into this conical flask. So I have taken out the solution and I will press this E button now, which is here. You can see this E button. Here is the E button. I will press this E button and this solution will start draining. So you can see the solution is going into this flask. So in this way we have transferred our Fa2 25 centimeter cube into the flask. Now the next point says add a few drops of bromothymol blue indicator. This indicator is blue in alkali and yellow in acidic solutions. We have taken Fa2 through pipette into the conical flask, and Fa2 is our sodium hydroxide alkaline solution. So in alkali, this bromothymol blue will be blue. So let's add few drops of bromothymol blue first. So here is our bromothymol blue, and by using this dropping pipette, if a dropper is not already there, you can use this dropping pipette, or else there is always a dropper in the indicator solution. So we will add few drops. Now, what is meant by the term few drops? Few drops means 3 drops maximum. 3 drops. Few means 3 drops. 1, 2, 3. So 3 drops, and we have seen that the solution has turned its color to blue. Now the next point in the method is perform a rough titration and record your burette readings in the space below. So we will record first the initial burette reading, and then we will perform a rough titration. So the initial burette reading is 0.00. Now we will start adding Fa1 solution from the burette by opening this tab and continuously swirl this, and look for the solution as soon as it turns yellow, which can easily be seen over the white tile. We will stop. No, it's not yet yellow. Now we can see the solution is completely yellow. We have stopped. This is our rough titration. Now this is the yellow solution where I have stopped adding Fa1. Now look at the reading, and exactly where is the reading? If you look closely, the reading is at lower meniscus. The reading is exactly at 28.80. Final burette reading is 28.80. So the rough titer is 28.80. The next part says carry out as many accurate titrations as you think necessary to obtain consistent results. So first of all, let us see what is consistent results. Consistent results means the volume of titer used must be within 0.1, means it should be equals to or less than 0.10 apart from each other. Consistent result means 2 volumes used which are not more than 0.1, not more than 0.1 far away from each other. So let's repeat this, but before that, let me draw a table and see how these 7 marks are allocated in this table. So here is the comprehensive table which must be holding final burette readings in centimeter cube, initial burette readings in centimeter cube, and the volume of Fa1 used in centimeter cube, which can be calculated by subtracting these 2 values, and the best results. Now let's start for the first accurate titration. So before I start the accurate titration, I need to empty this flask first, and I will rinse it. I will empty this flask and I will rinse this with distilled water or tap water. Now I have to refill the burette again because it's used up till 28.80 volume. So I need to put this funnel again, Fa1 solution again, but this time I do not necessarily be reaching at exactly 0. I can take any value that is lesser in number than 20. So in this case, I have taken the value near to 2. I will record just now. I will record the initial burette reading also. And now I will take 25 centimeter cube of Fa2 again using this pipette filler. We will fill this pipette. Here is our Fa2. Up till the mark again, we will take it and we will pour it into this washed conical flask. E for eject, and as soon as the solution is empty, we will again add few drops of indicator. We have learned that 3 drops must be added. So 1, 2, 3 drops again. Now I will start accurate titration, but before I start with accurate titration, let me record the initial burette reading. Initial burette reading is 2.25. So you can see the lower meniscus is in between second and third graduation. Therefore, we will take it as 2.25 as an initial burette reading. Now, before I start accurate titration, let me tell you one more thing about accurate titration. Accurate titration means you do not need to add even few drops extra from the burette. Now, how can we achieve this? Initially, we have found that in rough titration, we have 28.80 centimeter cube volume used. Therefore, this volume now for accurate titration must be lesser than that volume. So as soon as I will start pouring in the solution, I will stop adding near this 28.8 mark. So I am adding it a bit faster till I reach 27, 28. And then I will stop this, and now I will open this. You can see I will open this and drop wise I will add. So now if you see, I will add here drop wise and I will continuously swirl this flask so that as soon as the solution goes blue to yellow, I will stop, and that must be the accurate titration. Do not panic if it is taking a bit more time. Do not rush and open this knob faster. No, just wait and be calm. It will turn yellow, and it is now yellow. You can see the contents are yellow and I have stopped. So this is my accurate titration results. Now this is my final burette reading, and we can read from here that it is 30.55 because again it is in between 5th and 6th graduation. 30.55. So I have recorded here the final and initial burette reading. Now I will subtract these two readings to get the volume of Fa1 used. So the volume used here is 28.30, which you can see is actually lesser than this 28.80. So this is your accurate titration result number 1. Now let me repeat the procedure again to take the second reading, initial and final, and do the same procedure to get a consistent result. So upon repeating the experiment for the second time, the volume of Fa1 used was same as in the first experiment. Therefore, these two values will be considered as consistent results, and we will use these two values. We do not need to proceed for the third time. Now, let's move on to the next part, which says, from your accurate titration results, obtain a suitable value to be used in your calculations. Show clearly how you obtained this value. Now, we got two readings same. It means we can write the average of these two here. That is the mean value to be used here in this part. But these two values will be added and divided by 2. And we need to write this here. Why? Because they have said show clearly how you obtained this value. So whether or not you are getting the two same values, you have to show them this way: 28.30 and 28.30 divided by 2 for the average means you are getting the same value, 28.30. Now let's proceed on to the next part. Part C1. Show your working and appropriate significant figures in the final answer to each step of your calculations. Appropriate significant figures means 3 significant figures as minimum, and for accurate calculations you have 4 significant figures to follow. Now, part 1 says calculate the number of moles of sodium hydroxide present in the volume of Fa2 pipetted into the conical flask. So we have pipetted out 25 centimeter cube of volume of Fa2. So here we can see that the Fa2 is 0.1 mole per dm cube solution, and we have pipetted out its 25 centimeter cube volume. So we will use the formula of moles. So the relationship of concentration and moles is concentration is equals to amount of substance in moles divided by volume of solution in decimeter cube. Now we have taken the concentration as 0.10 and moles to be calculated divided by the volume we have taken was 25, but it was centimeter cube, therefore you need to divide it by 1000. So the calculated moles of sodium hydroxide are 0.0025 and 0 for 3 significant at least. The next part says use your answer to C1, that is this one, moles of sodium hydroxide, and the equation on page 2 to determine the number of moles of organic acid HA used to neutralize 25 centimeter cube of Fa2. So to neutralize this much moles of sodium hydroxide, on the previous page they have given you the equation which says 1 mole of HA reacts with 1 mole of sodium hydroxide. So they react in 1:1 ratio. Therefore, in this case, when the moles of sodium hydroxide are 0.00250 in 1:1 ratio with acid, its moles will be also 0.00250. Next part says use your answer to B and C2 to calculate the number of moles of acid in 1 decimeter cube of Fa1. Now in part C2 we have calculated the moles of acid which were actually present in the equivalent volume used for titration, and that was actually here in the part B, 28.30. So the moles we got in part C2 are actually present in this volume 28.30 of Fa1, that is acid. We will use this ratio to calculate the moles in 1 decimeter cube, and that is 0.00250 moles are present in 28.30 centimeter cube of volume. Therefore, how many moles will be present in 1 decimeter cube? Now 1 decimeter cube means 1000 cm cube. So we will use the same relation, centimeter cube. So we will write here 1000 cm cube. How many moles will be present in 1000 centimeter cube? So here if we calculate, we will get the answer 0.088 0.83 up to 3 significant figures. Now let's move on to the next part, which says calculate the relative molecular mass MR of organic acid HA. Now in order to calculate the MR of this acid HA, we need to use two pieces of information here. Number one, moles of acid present in 1 decimeter cube, and the previous page says the mass of acid present in 1 decimeter cube. So mass divided by decimeter cube means concentration, and moles divided by decimeter cube means also concentration. So how we relate these two concentrations? By this formula, that grams per decimeter cube becomes mole per decimeter cube when you divide it by the MR of the compound. The concentration changes to moles per dm cube. Now in the above part, the concentration in moles per dm cube is 0.0883, whereas in the previous page the data said concentration in grams per dm cube is 13.1 grams per dm cube. So once we calculate the MR in this way, the MR will be 148.3. Now 148.3 is up to 4 significant figures, and we were taking 3 significant figures in our previous calculations. Why I have taken 4 significant figures? Because if we look at the periodic table, the ARs are always given up to 1 decimal places. Therefore, we write the AR and MR of our compounds up to 1 decimal place. Now, let's move on to the next part, which says a student carrying out this method correctly with the same concentration of reactants obtained a titer of 28.30. Would this give a larger or smaller value of MR than yours? As coincidence, we got the same titer value of 28.30. Explanations which you can say. Number one, in our case, we got the same titer value. So we will just say no change. Why? Because we got the same value. No change, since my titer is same. Now let's think of a bigger or smaller titer value. Now first of all, see where this titer was used in the calculation of MR. So this 28.3 is used in 2 steps in the calculation of MR. Firstly, it was used in denominator to calculate the concentration, and then this concentration is again used in denominator to calculate the MR. Now think, if my titer would be greater than this, my titer would be greater than this, that means my concentration calculated here would be smaller. And if my concentration would be smaller, then this student's concentration would be greater. And if he has a bigger concentration, it means the calculated MR will be smaller. Let's say your titer is, for example, 30 centimeter cube. Then what can you say here? Then the student's titer here is smaller than your value, and if this value becomes smaller, then he must have got a bigger concentration here. So his bigger concentration means again here the smaller MR. So we will write here students' MR will be smaller due to higher concentration, and vice versa. If your titer, think of your titer is a smaller value, which means let's say 26.00, then what could you say? If your value is smaller and he must have got a bigger value here, it means the smaller concentration will be calculated for him, and for him a smaller concentration means bigger MR will be calculated. So here we can say then students' MR will be greater than ours. Why? Due to a smaller concentration. So here we comes to an end of 13 marks simple acid-base titration from May-June 15 variant 3.3.